Okay, this is section 3.2, and we're going to be talking about exponential functions. Suppose you have a new job and they gave you two options. You could either make $1 million for your first month, or starting at 2 cents a day, your pay will be doubled each day for 30 days. And so the question is, what would you pick? Now, you may have heard this one before, but 2 cents a day that gets doubled every day by the end of the month. Let's see what happens. So you start out with 2 cents, then next day you get 4 cents, then 8 cents, then 16 cents, then 32 cents. It's not looking good now. 64 cents, $1.28, $2.56. We're building up a little bit of steam here. $5.12. $10.24 by your 10th day. Wow, $1 a day. Not much. Now $20.48, $40.96, $81.92, $163.84. That seems like a big jump. $327.68. You're doubling it again. Now you're up to the $6.50. Wow, now you're in the thousands by your 17th day. Now the 2000s, 5,000 on your 19th day, 10,000 on your 20th day, 20,000 on your 21st day, 41,000 on your 22nd day, then 83,000, 167,000, 335, 671,000, 1,000,000, 342, 177.28, 2,000,000, 5,000,000, 10 million. So if you took the 2 cents a day, you were very smart, because this is what's called an exponential function. It is a function where x is in the exponent. And this is what true exponential increase looks like. Okay. As x increases gradually, f of x increases very quickly. So as you go along on your x-axis, minding your own business, you're not going very fast, boom, the function shoots up to infinity. Okay, this is what an exponential function is. So when people talk about it grew exponentially, usually they don't really know what they're talking about, but this is what it originally meant. This is what exponential increase looks like. So we've talked about linear and polynomial functions, where we had the variables x and y with positive integer exponents. X and y were in the numerator. We talked about rational functions where x and y could have negative exponents. That is, they could be in the denominator. And now, like I just said, we're going to be talking about exponential functions where the variable is in the exponent. And that table that we just looked at displays the function f of x equals 2 to the x power. On day 1, it was 2 to the 1. Day 2, 2 squared. Day 3, 2 cubed. And so on until on day 30, we had 2 to the 30th power. So the definition of an exponential function, let b be a constant real number such that b is greater than 0 and b is not equal to 1. Then for any real number x, a function of the form f of x equals b to the x power is called an exponential function of base b. So let's look at f equals 2 to the x as a graph. If you put in -2 for x, you will get 1/4 for y, because 2 to the -2 power is 1 over 2 squared, which is 1/4. If you put in -1 for x, you get 1/2, because it's 1 over 2 to the first. And then if you put in 0 for x, you're just going to get 1, because anything to the 0 power is 1. Put in 1, you get 2. Put in 2, you get 4. And so on. This is a curve that on the left side of the y-axis, when x is getting more and more negative, it's just approaching 0, because it's just becoming the fraction 1 over 2 to the x power. So the denominator is just getting bigger and bigger, and you're approaching 0. On the right side, the function increases rapidly as x increases gradually. By the time you get to an x value of 5, the y value will be 32 already. So it's shooting up quickly. That's what an exponential function looks like. If the base is a number greater than 1. So 2 is the base on that. That's what that kind of function looks like. If your base is between 0 and 1, something like 1/2 or 1/3, something like that, it looks a little bit different. All right, so let's look at g of x equals 1/2 raised to the x power. If x is -2 now, that's going to flip that fraction and it becomes 2 to the +2, which is 4. So now when you are at -2, you're up there at 4. When you have -1 in this function, it flips the function upside down. It becomes 2 to the +1, so you have -1, 2. When x is 0, you still have 1 for your value because anything to the 0 power is 1. Now, when x equals 1, you get 1/2. When x is 2, you get 1/4. And so now you can see the function has been flipped across the y-axis so that now it approaches the x-axis on the right side of the y-axis when x is positive, and it shoots up to infinity on the left side of the y-axis. Because now as x gets more and more negative, you flip the function and you're getting 2 to some bigger positive exponent. So when the base is greater than 1, it shoots up on the right side of the y-axis. When the base is between 0 and 1, it shoots up on the left side of the y-axis. Okay, so this is what I was just saying, is that if you have an exponential function and if b is greater than 1, if your base is greater than 1, then f is increasing and is sometimes called an exponential growth function. So I'm talking about that function on the left there, that as x gets bigger, the function increases. It's increasing and increasing. If, however, b is between 0 and 1, like 1/2, then the function is decreasing and is sometimes called an exponential decay function. That is that function on the right where it is decreasing. All right, the domain is the set of all real numbers. You can put anything in there for x that you want to. The range is always going to be 0 to infinity because the base cannot be negative. If the base of an exponential function was negative, it would just flip-flop back and forth, because if you have a negative base and you raise it to an odd power, you get a negative number. If you raise it to an even power, you get a positive number. So it just flips back and forth. So the range is just 0 to infinity. The line y equals 0, the x-axis, is a horizontal asymptote because the function, there's nothing you can raise a positive number to, no power you could put on a positive number to get 0. It's never going to happen. The function passes through the point 0, 1 because f of 0 is b to the 0 power, which is 1. The value of the base of the function affects the speed at which the function rises or goes down. So the speed, meaning as you move along the x-axis from left to right, is it shooting up very quickly or is it shooting up less quickly? That all depends on how big the base is. If it's 3 to the x power, that's going to shoot up a lot quicker than 2 to the x power. Because by the time you get to 4, if you're doing 3 to the x, that's already up to 81, whereas 2 to the x would only be up to 16. Okay, translations for these kinds of functions work exactly the way they did for any other kind of function. If you have the function y equals 3 to the x, that red function right there, and you subtract a positive number from the x part of that function, it will scoot the function to the right 2 spaces. And then if you add something to the whole thing, so 3 raised to the x minus 2 power plus 4 to the whole thing, that's going to move that function up 4 spaces. So you get the green function. Okay, Euler's constant. What is that? The value of the expression 1 plus 1 over x, that quantity raised to the x power, approaches a constant as x approaches infinity. Its value is approximately 2.718281828, and we represent it with the letter E in honor of Leonhard Euler, who was one of the greatest mathematicians of all time. He lived in the 18th century, 1707 to 1783. He was a Swiss mathematician, and he made enormous contributions to a wide range of mathematics and physics, including analytic geometry, which is graphing, functions, stuff like we're doing now, trigonometry, geometry, calculus, and number theory. And he is known for coming up with the idea of calling that number that we can't really express, that number that you always get when you divide the circumference of a circle by its diameter. he came up with the idea of calling that number pi, and for coming up with also function notation, which we've been using, f of x, to show you the value of a function, a certain location on the x-axis. So this number, we call it e. You will see it on your calculator. It's a little e. So why is e even a thing? Who cares? Because e shows up in many natural situations involving exponential growth and decay, the growth of interest-bearing investments, so we're talking about banking, population growth, that's medicine, city planning, agriculture, and many other kinds of growth and decay. So we're going to talk about this growth of interest-bearing investments. Now, for some of you, this may be something you've heard before. You know what it all means. But when I was your age, I had no idea what all of it means. I still have trouble understanding it today. So I'm going to give you a simple explanation. Hopefully it'll be simple and it will make some amount of sense. So when you put your money into the bank, and that money you're putting in is called your principal. When you put that money in the bank doesn't just let it sit in the vault. They loan it out to other people. And those people, when they pay it back, they have to pay back more than what they borrowed. They have to pay back what they borrowed and a certain amount of interest. So they borrowed your money and now they have to pay back your money and more money, some percentage of that amount of money. So they have to pay all that back. And when that happens, the bank gives some of that money to you and you earn what is called interest on your money. So when you get your money out of the bank after a year, say, you get your own money back plus a certain percentage of your principal called interest. So that money, that extra money is called interest. And there is each bank, or sometimes all the national banks, have a interest rate. And that is the percentage that they multiply your principal by to see how much extra money they will give you. All right. So when you get your money out after a year, say, you come and get it, and you not only get P, your principal, but you also get R times P, some, 2% times your principal or something like that. And if you rewrite that with P factored out, that is P times 1 plus R. So you put your money in P, you come back in a year and take it out, and you not only get P, but you get PR. So you get that whole amount, P times 1 plus R. Now, what if you took the money out and you immediately stuck it back in the bank? You stuck all of it back in, not just what you put in the first time, but all the interest too. You stick it back in the bank and wait another year. Well, after that year goes by, you're going to get back the same, it's going to be the same situation. You're going to get back the P times 1 plus R that you put in, plus you're going to get R times that amount. So you'll get even more money back. If you take that P times 1 plus R times 1 plus R and put it back in for another year, it'll get multiplied by 1 plus R again. And so you can see what's happening every year. If you take it out and put it back in, take it out and put it back in, you're getting more out, you're putting it back in, and now you're getting that interest rate multiplied by a bigger amount. And so each time you're going to be getting more and more money back. And you can see that what's happening is we're getting this exponential function of P, your principal, times 1 plus R raised to the T power when T is the number of years. All right. Now, you don't have to do that. You don't have to keep going and taking it out and putting it back in, because the bank does something called compounding. So you don't have to do it. You go to the bank and you just leave your money in there. And what happens is you have the money that you put in, plus every so often they will what's called compound it. They will, every certain amount of time per year, they will take that money and they will apply the interest rate divided by how many times a year they do it. And they will add that to your money so that for the next period, you're getting interest on even more money. And so if they keep doing that, you have this formula right here where N is the number of times they compound it. So it's not 1 plus R now, it's 1 plus R over N. And so each time they do it during the year, say they do it 4 times a year, they're going to divide that interest rate by 4 if it's 4 times a year. And then it will be raised to the NT power. So 4 is getting compounded 4 times now. And then multiplying it by how many years you leave it in. So the point is that, many banks all over the world, they all have different amounts of time that they compound things. And so what they talk about when they talk about this in banking is they talk about continuous compounding. Imagine that you're compounding it an infinite number of times. It's getting compounded every single second. So you're always earning interest on the amount that you would have if you took it out right now. And so that formula turns out to be A equals P e to the RT, because we found out that 1 plus 1 over x raised to the x power gives us, as x gets really, really big, it gives us Euler's number. And so this is the formula that ends up when you have continuous compounding. And so you can talk about banking without having to know how many times a bank compounds it each year, because it really doesn't make that much difference. If they compound it 4 times or 12 times or 365 times, it's all pretty close to what it would be if you put it into this formula using Euler's number. So these formulas are, what you would want to know. The interest that you get back is equal to your principal times the rate, the interest rate, times the time you leave it in. That's simple interest. If they didn't compound it, if you went and got it, that's what you would have. Now, if they compound it, n times per year and the interest rate is r, then the amount you would get when you go to get it is your principal times 1 plus r over n raised to the nt. And then if it is compounded continuously, then the amount you get is A equals P e to the RT. So hopefully that gives you more of an idea of what's going on here. Some of those words, maybe you didn't know what they meant, but maybe you did. Anyway, we'll move on and do an example. So suppose that $5,000 is invested and pays 6.5% per year under the following compounding options. So A, compounded annually. So that's when they do it 1 time per year. We're going to use this formula. The amount you're going to get back is your principal times 1 plus r over n, where n is the number of times it's compounded. And if it's compounded annually, that means it's only compounded 1 time. So n is 1. All right, so you put that in, 1,000 for your principal times 1 plus the interest rate, which is 6.5% over 1, and then you're raising it to the nt power. So 1 is your number of times a year it gets compounded, and t is 10. It says how much would you have left after 10 years. So we're putting in 10, and if you multiply that out, you are going to get $9,385.69. All right, suppose you put it in and it's compounded quarterly, which means that they do it 4 times a year. They compound it as if you went and got it out and stuck it back in again. So then you'd have 5,000 times 1 plus the interest rate over 4 times a year, raised to the 4 times 10 power. If you multiply that out, you are going to get this, 9,527.79. C, if you get it compounded monthly, that means that they do it 12 times a year. So n is 12, and you would do that same exact formula. And now it will be raised to the 12 times 10. And so that comes out to be about $9,560.92. And then if you do it daily, that's going to make n 365. And if you do that and you multiply it all out and stick all the numbers in, then you are going to get about $9,577.15. Now you can notice that it's not that much difference over 10 years time between 9,385.69 and 9,577.15. I mean, it's just, not that much money. It's not that big of a difference. So if you put this all into Euler's formula, A equals P times e to the RT, if you have continuous compounding, then you plug that in, you're going to have 5,000 times e raised to the RT power. And if you punch that into your calculator, you're going to get 9,577.70 cents. Okay, and just to make sure you know how to punch that into your calculator, the first thing you're going to do is punch in 5,000, obviously, and then you're going to hit multiply, and then hit your left parenthesis and put in the exponent. So you'll multiply 0.065 times 10, and then you'll close the parenthesis with your right parenthesis, and it will come up to look like this, and then you'll hit second or inverse function, natural log, ln, and then it will look like this after you do that, and then when you hit equals, it will show you the answer. All right, moving on. So the half-life of radium, first of all, Marie Curie lived from 1867 to 1934. In 1898, Marie Curie discovered the highly radioactive element radium. She shared the 1903 Nobel Prize in Physics for her research on radioactivity and was awarded the 1911 Nobel Prize in Chemistry for her discovery of radium and polonium. Marie Curie died in 1934 from complications of excessive exposure to radiation. And if you don't know what radiation is when you have atoms that are very unstable and they start getting rid of some of their electrons or protons or neutrons, and they just start getting rid of stuff because their nucleus is not balanced and they're freaking out and they're just throwing things out. And even though you can't see those little particles, they hurt you. And that is why you get killed. So radiation sickness is what that is. It's when your body's being destroyed by tiny little protons, neutrons, and electrons that are being thrown out of these kinds of elements like radium. And so radioactive elements are constantly breaking down, and they're even changing what they are. They change from a certain kind of element to a certain other kind of element because they're getting rid of electrons and protons, and that's what makes an element what it is. Anyway, moving on, the half-life of radium. So when something is breaking down constantly, it's decaying. And so when we talk about the half-life of a radioactive material, that means how the time it takes for half of the original amount of a substance to turn into something else. So after each half-life, the amount of the original substance decreases by half. So this says that the half-life of radium is 1,620 years. And this is how they do some kinds of dating of old objects. They're trying to figure out how old it is. They can look and see how much radium is in there and how much there was in the beginning, and then they can figure it out because every 1,620 years, half of the radium in there goes away. So in a sample originally having 1 gram of radium, radium-226 is a kind of radium with a certain number of protons. The amount A of T in grams of radium-226 present after T years is given by A of T equals 1/2 raised to the T over 1620. And I'll tell you what the general formula is for figuring out how much of any kind of radioactive element will be left after a certain number of years in a minute. So T is the time in years after the start of the experiment. How much radium will be present after 1,620 years? Well, we already know the answer to that because that's the half-life, so half of it. And they started out with 1 gram, so there'll be 0.5 gram left, but I'll go ahead and show you how that's done. A of 1620 is equal to 1/2 raised to the 1,620 over 1,620. And so that is just 1/2 to the 1, which is 1/2. So 0.5 gram will be left after that many years. B, how many will be left after 3,240 years? That'll be 1/2 raised to the 3,240 over 1,620. That's 1/2 to the second power, which will be 1/4. So 1/4 of a gram will be left. Part C, how much will be left after 4,860 years? Same formula, you just put in a different amount for T, and that will be 1/2 to the third, which will be 1/8 of a gram. So in general, the amount of a radioactive substance remaining after a certain amount of time is modeled by the function f of t equals m times 1/2 to the t over h, where m is the initial mass, so however much you started with of the substance, raised to the t, which is the number of years, divided by h, the half-life of the substance. So the book didn't actually give that particular formula. It just did a couple of examples and didn't really tell what the general formula was, so I wanted you to know that. I think that's it. Yep, that's all. So sorry for belaboring a few things, but thought you might want to know. And I will be putting up the homework very soon. Thanks for listening. Bye.